All right, so today we're going to learn how to factor the first of our two special factors. Tomorrow we'll have something called the difference of two squares. Right now we're going to learn how to factor something called perfect square trinomials, or perfect squares. Now, a perfect square trinomial will be in the form of a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. Believe it or not, a and b are not variables. And then once we get good at factoring, well, as we get good at factoring, we're also going to solve equations by factoring perfect squares. All right, now, polynomials can be perfect squares just like numbers can. But first, let's talk about some numbers. What is a perfect square? Well, it's something squared. Okay? And I almost literally wrote something squared. Then I thought I'd go ahead and put a number. But anything that's squared, the result is a perfect square. Okay? So when we're talking about numbers, we're talking about 1 squared, which is 1. 2 squared, 4. 3 squared, 9. 4 squared, 5 squared, 6 squared. So 1, 4, 9, 16, 25, 36, 49, 64, and so forth are perfect squares. Okay? Does this list ever end? No, you just stop writing it, but it never ends. Okay? Because all you got to do to get the next perfect square is square the next number. All right? Now, technically speaking, fractions and decimals can also be perfect squares. They're just kind of awkward, and I didn't make a list of them. But for instance, if you take 1/2 and you square it, what do you get? 1/4. 1/4 is a perfect square. If you take 1/3 and you square it, what do you get? 1/9. And look, here's why I didn't try to make a list. What if you take 2/5 and square it? What do you get? Now, notice something in this short little list. When a fraction is a perfect square, notice that its numerator is a perfect square and the denominator is a perfect square. Okay? So that's how you can tell if a fraction is a perfect square. If both parts that make up the fraction are perfect squares, the fraction's a perfect square. Okay? With decimals, it's even more difficult to tell. Now, some simple ones, you can tell. Like if I did 0.5, since 1/2 squared is 1/4, you could probably guess that 0.5 squared is 0.25. Well, what's 0.46 squared? I don't know. Would you have ever guessed that 0.2116 is a perfect square? It is. Its square root is 0.46. So, we're not going to try to memorize all possible fractions. Fractions are easy. Decimals that can be perfect squares. Whole numbers, yeah. We need to know up through 169 pretty well without thinking about it. Okay? Now, here's how I got the form that I showed you right here that the perfect square trinomials take. If you take a plus b and square it, to square a binomial, to square anything means to multiply it times itself. So that means a plus b times a plus b. Well, FOIL method, you get a squared plus ab plus b squared, which is a squared plus 2ab plus b squared. Same thing happens if there's a minus sign between them, except that's a negative, therefore that's a negative. Okay? Now, a and b, don't think of those as variables. Think of those as terms. You've got a first term plus a second term, and then you square that binomial. The result is the first term squared plus 2 times the first term times the second term plus the second term squared. Or you get the minus. Okay? Now, okay. What we want to do is we want to be able to go backwards. Let's see. All right. So your perfect square trinomials look like a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. Three things have to happen for you to know that you have a perfect square trinomial. The first term of the trinomial has to be that first term of the binomial squared. So the first term has to be a perfect square. What do you think is true of the last term of your perfect square trinomial? Same thing, right? It also has to be a perfect square because it's that second term of the binomial squared. So it has to be a perfect square. And then the third condition. Checking the first two conditions, that's fairly simple. But the third condition is that bx term has to either be plus 2ab or minus 2ab. And here's where it gets a little tricky too. That first term that has to be a perfect square, it's a squared. It's not a, is it? It's a squared. That last term that has to be a perfect square, it's b squared. It's not b. So you've got to figure out what a is, what b is, and then make sure that 2 times a times b is what you have there in the middle. All right. So first thing we got to be able to do is recognize when we have a perfect square and when we don't. Because if you try to apply this to something that's not a perfect square, it won't work. All right, so determine whether each trinomial is a perfect square trinomial. So A here, is 4y squared a perfect square? Yeah, it's what squared? It's 2y squared. Is the last term, 9, a perfect square? It's what squared? It's 3 squared. Is the middle term equal to 2ab? Is the middle term equal to 2 times, what would a actually be? Not 4y squared. A would be 2y times b, 3. Is our middle term equal to 2 times 2y times 3? Yes. Since all three conditions are met, yes, that one's a perfect square trinomial. Now, so what? So what? That means this, that 4y squared plus 12y plus 9, remember, where was it? Was it here? No, here. We've got this, don't we? So we've got to be able to go backwards and arrive there. Or there. I'm good either way. Okay? So we should get a plus b times a plus b. A plus b times a plus b. Now, with numbers, you wouldn't leave that, right? You would not leave 5 times 5. You'd write it as 5 squared. We can do the same thing. Instead of 2y plus 3 times 2y plus 3, write it as 2y plus 3 squared. Questions? All right, now, I'm going to tell you something I probably shouldn't tell you. Could you factor that even if you never recognized it as a perfect square trinomial? Yeah, you can. So why are we learning this? Because it's easy. No, scratch that. Wrong word. Because it's fast and it's efficient. Okay? It's fast and efficient. And when you get the next 180 problems to work, you want to do them the long way or the quick way? Just saying. All right. Part B. Is the first term a perfect square? It's 3x squared. Is the last term a perfect square? It's 2 squared. Is the middle term, now it's negative, that's okay. Is the middle term negative? Is it negative 2 times 3x times 2? So this one is not a perfect square trinomial. It may or may not be factorable, but it's not a perfect square trinomial. Okay? Any questions? Well, not for this. All they wanted us to do was decide if it's a perfect square trinomial. The only reason I factored it out was to give you an example of how to factor a perfect square trinomial. All right, let's try this one. X squared plus 10x plus 25. First term is x squared. Last term is 5 squared. Is the middle term 2 times x times 5? Yes, so this one is a perfect square trinomial. So I don't need the chart. I know that the factorization is a plus b times a plus b. X plus 5 times x plus 5. With me? It seems like magic if you're not. But I decided that that was x squared. That's 5 squared. So a is x, b is 5. In the middle is 2 times x times 5, so it is 2ab. So I decided all that almost instantly, didn't I? So it's x plus 5 times x plus 5, which you can write as x plus 5 quantity squared. Okay? Now, what if there was an equal 0 there? Yeah. We've done this next step several times this year. Can't I take the square root of both sides of an equation? The answer to that is yes. Well, the square root of something squared is the something. So the square root of that binomial squared is the binomial. What's the square root of 0? 0. So what does x equal? We only got one answer this time. Since these two binomials are identical, we would get x equals negative 5 twice. Well, if it equals negative 5, it equals negative 5. You don't have to say it again. So for a perfect square trinomial, when we solve that equation, we just get one answer instead of two. Now, in Algebra 2, you'll learn that you actually do get two answers. They're just not unique. Unique means each one different. You get negative 5 twice. Okay? You with me? All right. We can use that same technique to solve quadratics in a brand new way. Up until this moment, the only way to solve 4a would be to square that binomial on the left, subtract 121 from both sides to get it in ax squared plus bx plus c equals 0 form, factor it, and go from there. But let's follow the model that we just came up with on the previous example. I can take the square root of both sides. The square root of a minus 10 quantity squared is a minus 10. The square root of 121 is 11. What does a equal? Okay. Do 4b using that technique. Do you want to punch that in on a calculator? Yeah, I don't want to either. Okay. Could you have written z equals negative 3 plus the square root of 26? I'd be happy with that one too. Okay. Any questions?